Hello everyone, myself Shikha Patel from Department of Mathematics, IIT Patna, India. My title of presentation is Structure of FqR linear theta delta theta cyclic course. So these are outlines of my presentation. First of all, I will discuss some basic definitions like linear course, Hamming distance, dual code of a code, and cyclic course. After that, our main work FqR linear theta delta theta cyclic course. Its construction, theta delta theta cyclic course are in R, then FqR linear theta delta theta cyclic course, and then finally grammar for the construction of optimal codes. For linear codes, let F2 be the finite field and F2n denotes the set of all ordered tuples represented like in this way A1, A2, An, where each AI is coming from F2. The elements of F2n are called the vectors or words. A linear code over F2 is the subspace of F to the power n for some positive integer n, and a subset C of F to the power n is linear if and only following these two conditions will hold. That is, its linear sum is in C and its scalar multiplication is again in C. For example, suppose C is a code consisting of these elements, then we can see that this is a linear code over the finite field F2. Now the Hamming distance between any two code words x and y of C is the number of positions in which these two vectors will differ, and it is denoted by pxy. Further, the minimum distance of a code C is the minimum of the minimum Hamming distances between any two distinct code words. For example, let's see with a set consisting of these vectors, then we can see that the minimum distance of the code C is 2. Now, if C is any k-dimensional subspace of F to the power n, then it is an NK code, and if we also specify the minimum distance, then it is an NKD code. Dual code of a code. For this, we consider the inner product of two vectors V and V in F to the power n. This is scalar defined as U1, V1 plus U2, V2, and so on. U1, V1. If its inner product is 0, then these two vectors will be called orthogonal. For a linear NK code C, its dual is denoted by C perp, and it is defined as a set of those vectors of F to the power n which are orthogonal to every code word of C. For the cyclic code, this is a linear code, and also any cyclic shift of a code word is again a code word. That is, if A0, A1, An minus 1 in code word is in C, then its circular shift An minus 1, A0, A1, and so on, An minus 2 is also in C. For the construct, to discuss the algebraic properties of a cyclic code, we must identify a vector A0, A1 in F to the power n with the polynomial AX, which is defined as A0 plus A1x plus and so on, An minus 1 F to the power n minus 1 in this quotient ring, F2x modulo F to the power n minus 1. That is, we can always view a code as a subset of F to the power n as well as a subset of Rn. So, for the construction of cyclic codes, we consider the set generated by fx. That is, this is the set consisting of the all multiple of fx where Rx in Rn. For example, suppose C is a code generated by 1 plus x square in R3, where R3 is F2x modulo x cube minus 1. So, we can generate a code by just multiplying 1 plus x square by each 8 elements of this ring R3. So, here we get only 4 distinct code words: 0, 1 plus x square, and x plus x square. This is now from the algebraic and combinatorial structure, we can easily get the code C. In the terminology of ring theory, we can say that these cyclic codes are ideal in Rn, and these ideals are principal ideal that is generated by a single element. Now, cyclic codes are constructed over the commutative structure. Now, people are continuously searching for the structure or the technique where we can improve the Hamming distance, that is, optimize Hamming distance. For this, we are considering a non-commutative setup. For this, we consider a set Rx theta where theta is an automorphism. This set form a ring under the usual addition of polynomials, and multiplication is defined as axi star bxj is equal to a theta to the power I b x to the power I plus j. This is a non-commutative ring unless theta is identity. A linear code C of length n over R is said to be cyclic code under this automorphism theta if and only for any code word C in C its cyclic shift is again in C. That is defined as theta Cn minus 1, theta C0, theta Cn minus 1, theta Cn minus 2 is again in C. This is the progression of the coding theory. So, firstly, linear codes were studied over the binary field. Then, in 2007, Voucher et al. Investigated is the cyclic force, that is the cyclic force over the non-competitive structure, and these are investigated further in 2009, and in 2010 Bobbitt et al. Studied Z2Z4 linear force, that is the force over the mixed alphabet. In 2014, Abulab again investigated Z2Z4 cyclic force and derived its dual also. In 2000, et al. Analyzed the additive forms of cyclic force. Additive force over this structure, Z p to the power s, Z p to the power r, Z p to the power s in general, and further they analyzed over the mixed alphabet with three alphabets, Z2, Z4 and Z8. Further, in 2020, apart from these works, Belcam et al. Studied force over the mixed alphabet in the non-competitive setup. Now, these works are in the non-competitive setup, but here we will also consider this two polynomial ring with both theta and derivation. So, Gauss and Laurie studied sigma delta force and introduced the notion of F sigma delta force. In 2014, Voucher et al. Studied linear force by using the polynomial rings with the help of both automorphism and the derivation. In 2018, Sharma et al. Investigated these cyclic force with the derivation over this particular ring, and in 2021, Amma et al. Studied sigma delta skew quasi-cyclic force over the same ring. Recently, in 2021, Patel and Prakash studied theta delta theta cyclic force over this ring via the decomposition method. Now here we will study the theta delta theta cyclic force over the mixed alphabet FqR. For this we consider a ring FQ U modulo U square minus 1, and let's see the linear code of length n over R, and these C1 C2 are the linear codes of length n over FQ, and mu1 mu2 is defined like this way. These mu1 mu2 are the orthogonal decomposition, idempotent orthogonal decomposition of this ring. That is, R can be decomposed as mu1 FQ direction mu2 FQ. That is, any element of R can be represented like this way. R is equal to mu1 u1 plus mu2 u2, and C is represented as mu1 c1 direction mu2 p2. So now we will define the theta derivation. So this is, if these two conditions will hold, then this map delta theta is a theta derivation of R. We consider here the set FQ as theta delta theta. Then this ring is a non-competitive ring under the usual addition of polynomial, and multiplication is defined like x is equal to sigma ax plus delta a, here a belongs to FQ. Further, we extend this to this in general over the ring R, where theta is the Frobenius automorphism of R defined by theta of a plus ub is equal to theta a plus u theta b, and delta theta is a theta derivation of R. We define a map delta theta in this way. Delta theta a plus ub is equal to 1 plus 2 theta of a plus ub minus a plus ub, and consider the set FqR as, where a is coming from FQ and S belongs to R. This is, we can see that this is a ring but not in the R module structure under the usual addition. So for this we consider a map xi from R to FQ, xi R is equal to A, and introduce the R scalar multiplication on this ring FqR. That is, star is defined from R to FqR defined by R star AS is xi R A RS. Then it is verified that this ring R is an R module under this defined multiplication. So we can also extend this multiplication to FQ rho cross R tau. A non-empty subset C of FQ rho cross R tau is said to be an FqR linear code of length rho plus tau if C is an R submodule of this ring. Now we define the inner product between T and T dash, which is defined as U summation I is equal to 0 to rho minus 1 ai dash plus summation j is equal to 0 to tau minus 1 sj dash. So C perp is defined as T dash is any element in this ring such that T dash is equal to 0 for all, sorry, here T dash belongs to C, for all T belongs to C. Now we consider this ring R rho tau defined as FQX modulo ideal generated by f to the power rho minus 1 and Rs theta delta theta f to the power tau minus 1. Now we consider two polynomials Ax in this ring and Sx in this ring. Now we identify this code word in this ring FQ rho R tau with the polynomial of this form. Cx is equal to Ax, Sx belongs to R rho tau. Then the multiplication is star in R rho tau is defined as follows: Rx star Ax Sx is equal to xi Rx Ax Rx Sx. Now, this ring Rx theta delta theta is generated by Fx is the left, Rx theta delta theta module under this multiplication Rx Ax plus ideal generated by Fx is equal to Rx Ax plus ideal generated by Fx. A force C of length tau over the ring R is said to be theta delta theta linear code if it is left Rx theta delta theta sum module of this quotient ring, and a force C of length tau over R is said to be theta delta theta cyclic code if C is a theta delta theta linear code, as well as if for any forward C belongs to C, its T theta delta theta cyclic shift is again in C. Now let C be a linear code of length tau over R, where C1 and C2 be linear codes of length tau over F2, then C is a theta delta theta cyclic code of length tau over R if and only C1 and C2 are theta delta theta cyclic codes of length tau over F2. Further, if C is a theta delta theta cyclic code of length tau over the ring R, then C is generated by mu1 f1x, mu2 f2x, where f1 and f2x are the generating polynomial of Ci corresponding to the finite field F2, and its cardinality is q to the power 2 tau minus summation I is equal to 1 to 2 degree of phi x. And let C be a theta delta theta cyclic code of length tau over R, then C has a generating polynomial fx, which is a right divisor of x to the power tau minus 1 in this ring Rx theta delta theta. And now we will extend this work to in mixed alphabet, that is FqR linear theta delta theta cyclic codes. A code B is said to be FqR linear theta delta theta cyclic code of length rho plus tau if B is an R2 module of this ring, as well as for any forward A in B, that its T theta delta theta cyclic shift is again in B. Now for we consider an FqR linear code B of length rho plus tau. We define two sets B1 and B2 in this case, where Ci's are defined as in previous slides for I is equal to 1, 2. Also an FqR linear code B of length rho plus tau can be represented. That is, we can always decompose this code B over R into over F2. That is B1 plus mu2 B2. This is also an idempotent orthogonal decomposition. A code B of length rho plus tau over FqR is the theta delta theta cyclic code if and only be the left Rx theta delta theta sum module of this in R rho tau.
2 minutes left, Professor.
Yeah. Okay. Let B be an FqR linear code of length rho plus tau, where B1 and B2 be linear codes of length rho plus tau over F2. Then this code B is an FqR linear theta delta theta cyclic code of length rho plus tau if and only B1 and B2 are the corresponding theta delta theta cyclic code of length rho plus tau over the finite field F2. Let B be an FqR linear theta delta theta cyclic code of length rho plus tau. B is generated as this left Rx theta delta theta sum module of rho plus tau, and also this is generated by this polynomial fx, which is a right divisor of x to the power tau minus 1, and gs is a divisor of x rho minus 1. Now we define the gray map for, that is any arbitrary element of ring R is represented as R1, R2 and F2, and we also any element of FqR is represented as A slash this R1, R2 and let GL2 F2 be the set of all 2 cross 2 invertible matrices, and we define a gray map phi from R to F2 as follows: A plus UB goes to A comma B into L, where LL transpose is equal to gamma I2, and I2 is the identity matrix of order 2. We can also extend to now we define the gray map for the mixed alphabet, that is phi from FqR to F2 as follows: AR is equal to A R1 and R2. We can also extend this map to component wise over this ring F2 rho R tau. We can easily extend it to component wise. So this same phi is an F2 linear map, and distance preserving from F2 rho R tau to F2 rho plus tau. That is this also preserve the distance to Hamming distance. If C is an R rho plus tau plane DL FqR linear code, then phi C is the rho plus 2 tau KDS linear code over F2. This was under progress. These are the references.
Thank you, Professor Patel, for this nice presentation. Is there any question or comments? So we have a question from Professor Turan. So she asked, what is the Q in this ring?
Q is some prime power. Here P is odd prime. Actually, because mu1 and mu2 is defined as 1 plus u by 2 and 1 minus u by 2. So Q is any prime power. That is Fq we are considering. Fq is a finite field. So Q must be some prime power and P is an odd prime here. Because its decomposition is mu1 and mu2 and it is defined as 1 plus u by 2 and 1 minus u by 2. So it is always odd prime.
So thank you, Professor. Is there any other question? So we have another question. What about the generator polynomial of FqR?
So here we can always generate a code B in FqR like this way. Here Fx means this is the generating polynomial for this code B, that is FqR linear code. Fx is mu1 f1x plus mu2 f2x, where Fx is the right divisor of x to the power tau minus 1 and gx is the divisor of x to the power rho. Means this is generated by this form mx fx. Means these two polynomials. This is not singly generated actually. This is generated by gx comma 0 and mx comma fx, where fx is coming from our original code, that is from R, and this gx is coming from this fq. Means this is combination of these two, fq and R. So first time we consider when we consider fx, then we have to took the right divisor of x to the power tau minus 1, and when we consider gx, then this is simply the divisors of x to the power rho minus 1. That is, this is generated by the linear combination of these two.
So thanks again, Professor Patel, for your contribution. We have a limited time. Please make private conversation between Professor Turan.
This work is under progress, so I am exploring this. So I have to make some examples right now. This is under progress.
Okay, thank you again. Please stop sharing your screen.
Thank you.